Okay, so the topic for the today is encoder and decoders. So what exactly encoder and decoders? Why we needed that encoder and decoders? So in AI, there are a lot many different kinds of problems we have, but in that the one category of a problem is called sequential. Sequential. Sequential means when we have to deal with that kind of data which has the relations with the history or the past, such as time series. So we know that the times, if suppose we are just considering the sales data, so the sales for today is definitely going to depend on the whatever the sales it had done in the past days or the past months, or whatever the sales had done in the past, that is going to be impact on today or maybe in the future. Okay, and the other category is the text data. So when I'm saying text, it means, so we all know that there are some rules that if you are writing what after that, that is will come almost, if you see in the most of the scenario, in a 95% and 9% it will come what is. So there isn't dependency of this is, and or after that what that is will come. So there are lot many things dependencies in text data, like before the any like sentence, but you can say the vowel, so you have to use an before to that. So these are some rules which is getting dependent with the words, that when that word will come, when you have to use the verb first form, second form, or third form, like those kinds of dependencies are there. So to solve the sequential kind of problem, we have the different architecture to deal with. The first was RNN, LSTM, GRU. So this LSTM is a advanced version of RNN. Okay. So that's why when I was explaining the LSTM, I showed you the RNN as well. RNN has only one gate, but the LSTM has the three gates. So this is, RNN can handle the smaller text, but LSTM can handle the larger text. But it is slower. It is slower in a training. But GRU has little bit performance lesser than the LSTM, but it is faster training than LSTM because it has lesser gates than LSTM. Okay, so this is. But apart from these three architectures, why we needed this kind of architecture, which is called encoder and decoder? Why we needed that? So the reason is, what happened to these architectures? Again, these were not able to handle too long architectures or the too long text. So to handle those things, the new architecture or the new methodology or new way to use the LSTM is, they introduced and named as an encoder decoder. Encoder and decoders are not any, these are not the algorithm, these are the arrangement of the this LSTM, RNN, or the GRU. These are the arrangement. In a different way, they arrange the RNN, LSTM, and GRU, and they solve some specific kind of problem, like a longer dependencies problem in a time series or in a text. So how, if I will just uh, show you how this one will get. So how exactly the LSTM encoder decoder looks? So just understand on a high level. First, let me explain. This is encoder, this is decoder. Okay, and this is called, actually the center part which you are seeing it here, this is called context vector. Context vector, or somewhere people it says a summarizer. Okay, so this is, and here we will give the input, and here we will get the output. This is the output, and this is the input. This is how the, on a high level, the architecture of the encoder decoder. So usually when they introduced, so the paper was introduced for the, when they introduced this encoder decoder architecture, they introduced this for the machine translation, or you can say the language translation, and actually it performed very well than the prior algorithms of LSTM and all those things. Okay, now how it looks like. Okay, now let me show you. So there are multiple kind of problem, sequence to sequence. So what does it mean by sequence to sequence? Means you will give a input as a sentence, and output also I want a sentence. Sentence as an input, sentence as an output. And what would be the example? Language translation, or a reply. Like if suppose I wrote here, hi, how are you? And your algorithm should reply, I am good, or I'm not good, or I'm doing well, like that. I am doing well. So this kinds of, so this is also a sequence, input and output is also sequence. So to solve this kind of problem, we use encoder decoder. But for using encoder and decoder, there are three major problems were there. The first problem was the length of sentence will vary in input and output. Means sometimes, let's suppose you have a multiple records, like multiple records of a language translation data. Some, here it is written in English and here it is Hindi. Another sentence of English, Hindi, English, Hindi, English, Hindi. So let's suppose this sentence is of with 4 words, and this is output of Hindi is 5 word. It get difference in English and Hindi, or in any languages. It is not necessary that if in English you have a 4 words, when you translate into other language, that will also be in the 4 word. It could be in 3 word, it could be in 8 words. So that is, other is, here you cannot be sure that if this is for all, this one will be 4, this one might be 3, this one might be 8, this one might be 9, this one might be 11. So these are the problem. So how to handle that? So this part were already handled it. If you guys have ever read, or I will cover, there is a some concept called padding. Okay, so by using padding, we handle this issue. Like if your training data in input, if the lengths are getting varied with 4, 6, 2, 11, 10, so this will can be managed by using the padding. I will cover that in the next session. We will have the hands-on with the LSTM and the encoder decoder, and we will see the language translation, how we can do that. Sorry, it is not. It's not synthetic data. Let me show you. Tell you how it is. Let's suppose I have a this data set, and here this is English statement, and this is Hindi. So here, hi, how are you? Okay. Uh, Let me write this one. Okay. So this is hi, how are you? So, so this is aap kaise ho? This is okay. Now other sentences. My name is Ved. So मेरा नाम वेद है, ठीक है. Now if this is so, here if you see how many word are there, three, but here if you say there are four words. So just assume, usually machine won't understand the text, so I'll have to convert this into a vector. So assume that this how are you got converted in this 0 0.3, 0 0.2, 0.7. We will come on this vector that how it will generate it, okay, but just for imaginary time understand this is. And now like for each word, this is for the how, this is 0.3, for r this is 0.2, and for the u this is 0.7. And now for here it has generated for every word 0.1, 0.6, 0.23, 0.37. Now this one has the 4 and this one has the 3, then model will throw error. It model always expect any fixed dimension. That was the problem with the even encoder decoder. That was get solved by the transformers. So here in that case we need to perform the padding. Like what we will do, we will check in our entire this data what is the maximum length of the sentence. So if suppose one sentence is of 2 word, one sentence is of 5 word, so one sentence which has the maximum length is like 13 word, suppose in this your training records. If just imagine you have a multiple millions. So what I will do, I will add the zeros on the left part. Let's suppose here only 3, so the 10 times 0 I will add here, so it will become 13. If somewhere the words are of 8 length, so 5 times I will add the 0, so it will become 13. So all the length should be of the same length. Vector should be of the same length. So that is called the padding. And in that there is something called post padding and pre padding. Post padding means after the vector you are putting 0, or pre padding means before the vector you are putting the 0. That is the only difference. Okay. So this is what by the padding we covered. But the issue is sometimes by giving input 5, we are expecting 5 as an output. Sometimes I'm giving 4 as an input, but at that point the conversion is with the 3 words only. So it happens. So how to handle that part? That was a very so now let's understand that how it works. So usually if I will just show you here. So if this is the encoder, this is context vector, this is decoder. So if suppose I have written it here, how are you? So the output will be here, आप कैसे हो, right? And this is context vector, context vector. So this is okay. So usually in encoder how data goes, so first time what it will do, this entire word will not sentence will not go, this entire sentence will not go in one shot. If you remember in last class I said first time this word will go, okay, then this word will go, then this word will go, okay. And if once this entire word will go one by one to this encoder part, now encoder will try to understand some mathematical operations will happen here, some mathematical operations will get happen in the encoder, and it will try to summarize, and it will give one vector, this vector it will give whatever the values will be. I will come on that, what will be the dimension and everything, and that is known as context vector. So this is sometimes people say it as summarizer. So this vector whatever you will get it here, no, that is called the summarizer of the whatever the input sentence you have. So this vector will have the information, it has the entire information of sentence. Understand? So this is called. Now so this is also called token by token, you can say, or the word by word. So I'm saying, let's suppose here the first word will go as an input in encoder. Some mathematical operation will happen here. Then the next word will go R in that. Again, some mathematical operation will happen. Then the next word will go U. Some mathematical operation will happen. Then this question mark will go. Some mathematical operation. After doing these all mathematical operations for entire these four words, it will give you output one vector, and that vector is called the context vector. Understand? Mhm. No, no, it will not create a vector for the how until or unless the entire sentence will not go. This one will not create the vector. Just listen it carefully. I'm saying first how will go, mathematical operation will happen here. Then R will go, then U will go, and then this question mark will go. And then after this context vector will create. Yes, it will. That's what I'm saying. It has the entire information of the sentence. It will be for the complete sentence, not for the words. See, there are two things. One is called training, and other is called prediction or inference. So understand, the way you had trained your model, after that you can, in the same way you have to utilize. Now this is not the complete, so that it will understand that whether it has completed or not. How, when it will understand, while producing it or while the prediction or while generating the text, it should understand whether I have to stop or not. So that part will come here, that when it will understand, this is to clear whatever the input you will give, till what time it will take the input. If you will give the as a paragraph, it will continuously take until and unless the data you will not stop, it will not create the context vector. Yes, it will take the entire paragraph as an input, and once you will stop, then it will create the context vector. Yeah. So now here there is a one very interesting difference in encoder and decoder. Encoder will take that entire words sentence and then it will create the context vector. But what decoder will do, decoder will create the word if at every time stamp. It's not like that in decoder at the end it will create one vector and that you will convert into a sentence. No. Decoder will always create at the every time stamp. It will create word by word. Okay. So now let me formulate this in more in a depth and let's understand. So understand this very carefully now. So this is the LSTM. I'm not drawing the internal architecture of the LSTM. Just I'm showing, writing it here. Because internal architecture we have already covered. So this is encoder, okay? This is here LSTM, LSTM, and do not confuse that these are the three LSTM. This is one LSTM with different time stamp. If you had remember the last session, now if suppose I have a sentence, just allow me a minute, let me put into the charging. Okay, no issues, we'll see. So there is an word, how are you, and the sentence is aap kaise ho, and another is I am good, मैं ठीक हूँ. Okay, now this is the conversion English to Hindi. So first, how this data set will get converted? This one will be like this. How are you? In a token, I am good. So understand it's in a quotes. Okay, these all are in a quotes because it's a string. And the same will happen with this here. आप कैसे हो and मैं ठीक हूँ. So I am just putting it like this. Understand it? This one will get converted like this. Okay. So this is, you can refer it here. Now we know we cannot give word as an input to the algorithm. We have to convert this into a embedding or the vectors. So let us suppose this every word will get converted into a vector, like how got converted into a vector. So just how many total vocabulary are there? 1 2 3 4 5 6. So there will be 6 vectors. So one is for the how is 0, and less these all 5 will be the vector. Same for the R, 0 1 1 2 3 4. Okay, 6. And the same it will happen to the entire words till the good. How are you? And I am good. Okay, same thing will happen to these words also, but in here two things will get added in our data. For the before that every word, this token start, and here EOS will get added here also and here also. So the embedding for a start or the vector for a start will also get generated, and the embedding vector for the EOS will get generated. This one will also get converted into the vector. Okay, now to the algorithm, if you think, if I'll just here just encoder, and I'm just putting, okay. So first time this how what will go. So not how it will go, actually this vector. Actually this vector will go. Okay, and some random initializers of CT minus 1 and HT minus 1, hidden state and the cell state. And there are only two input, and then here R will go. Not R, the vector 0 1, and the same how are you, that will go, and it will produce a context vector. It will produce a context vector. Now what will happen here, this is very important, understand here. Assume here I have given first thing is start, and when you will give here a start, And a start means the vector, whatever the vector value for the start. Okay, whatever the vector value which has created, that will give input. So here it will, and we say that every time stamp it produces or it generated the output. So in output it will generate here a vector. Okay, it will generate the vector. And in decoder we use here a softmax. So what softmax actually do? So softmax perform, if suppose you have a 4 classes, 1 2 3 4. So for every value you will get some output like 0 0.3, 0 0.4, 0 0.1, 0 0.6. So what it will say for the given set of input, it will say this class is correct because this has the more probability. That what the softmax do. So let's suppose we give here the input vector of start and it produces one vector, and that vector has some value 0 0.2, 0 0.6, 0 0.3, 0 0.4. So what it will do, it will tell that whatever the word at position 1, that it will, the softmax will produce. Now it will get converted because it has the maximum. So what has the second word? How? R. So it will produce here R. Okay. Now this is your decoder. So it will give the two outputs here also. So this is how the training happens. And here HT and CT will go. And this input will also go as an, this output of the previous one will go as an input for the next. Now, so this R will not go. Just try to understand that vector is actually going. Okay. But if you would see here, this is not the correct generated output. Okay, this is wrongly generated. Actually, it should have generated the, I mean, not R here. Let's suppose a cache it has generated. Okay, let's suppose it has generated cache because we are doing English to Hindi, no? So it has generated cache. But actually, it should have generated up because that was the first word. But it has generated cache. I mean, the vector of cache it has generated in spite of generating the vector of up. And as per our knowledge we are passing the vector of cache to the next timestamp in the LSTM. So if the previous one had done some mistake, and that mistake if you will give as an input to the model, then the entire architecture will perform the same mistake and there is a no point of training. So what researcher and in the paper of encoder decoder they do, they introduce a concept called teacher forcing. Teacher forcing. They said it that while training we will not give this one as an input to the next timestamp. They said this one I will not give here. Whatever the exact or the original data we have, no, that we will give. Like see, we have a start. After that, I will not take this one. I will not take this one as an input. They said it. I have the original data. I have the original data. So from that, I will take here. I will try to add here up. And whatever it will again generate here, this one I will not give here into the next. I will give here cache. They will saying I will, because I'm training, I will give, while training I will give the sequences. So that is called teacher forcing. They will give the entire. Okay, and this softmax, in that softmax, the number of nodes. So this is understand it as a neural network. So the number of nodes in the neural network with the output as a softmax layer, output layer will be as a softmax layer. Okay, and the number of nodes will be equal as the vocabulary length of the output sentence. So vocabulary length is, let's suppose for the output sentence there are 5 word. So then there will be 5 neurons here at the output with the softmax layer. Okay, can you please mute? Someone is unmuted. So this is how the training happens in the decoder. Okay. Now tell me any question till here. Yes. Context was created by the encoder, and that context vector gave the input to the decoder, and then we have the data that for this kind of input what should be the output, and that we are starting it here. So understand, while training, when we are passing it a start, then whenever you will have a prediction time, a new sentence will come. That sentence, as it will reach the EOS, it means now it has to be stopped. It will not generate. No, no, we are not giving the pura sentence. We are giving just word by word. It generate word by word, word by word. Okay. If you remember how Chat GPT works, if you write something, I'm saying not layer. I'm saying that for the next time stamp, this is at the time stamp t. This is the t plus one. This is t plus two. So I'm saying that if suppose if I'll give the previous input here, and if this one has generated wrongly, then I'm giving the wrong input to the next time stamp to the LSTM. So now the entire training will be become completely wrong. So in spite of depending on the output, what I will do, because I have the original data, I will give the original input every time. Because since we have the data, right? We have the data here. Like this is how are you and this is aap kaise. We have the data. So that's why we are giving the data to train. We are not trying to depend that after giving this how are you, what was the first sentence generated. If suppose it generated here kaise, that one I will not give at the next time stamp to generate the new sentence, because let's suppose if I will give, it may generate here ho. So that's why while training it, we will give the actual whatever the first time stamp it has generated. Second time stamp I will give this one. Third time stamp I will give this one. Okay. So this is how it will work. First I give a start, then I give up, then I will kaise, then I will give ho, and then it will generate here EOS. Then it will stop. Okay. Now, so now understand. Let us suppose here. Oh, it's 11. Okay. So what we'll do? We'll cover the some part at the next session and the hands-on. Okay. Just understand. Yes, yes, yes. We will come after this. First, we'll understand the hands-on this. Then we'll go on that, and we'll surely go on that. So, how the back propagation happens now? The training. So, I think you guys are aware about the back propagation, maybe, but let me give you a brief. So, what is back propagation means? If this is your neural network, and if this is your any input, and it produces one output, input and output. So, with every input there is something called one is bias, it has introduced, and inside this there are two part. One is called linear and other is called non-linear. So in that linear, the equation is mx plus b. B is the bias, m is the trainable parameter, x is your input. And in the non-linear part here, at this part, this is your activation function, whether it is sigmoid or ReLU or lot many SeLU or whatever it is, tan H. So in that also some parameters are there. So how those parameters got changed? So this is the trainable part M and B. So how? So let's suppose for the given input 10, my actual data is saying the output should be 3, but my model has generated output 5, 4. So what is the loss? 4 minus 3, 1 is the loss. Now I will try to adjust this M and B, means this weight and bias in such a manner so that this loss 1 can be decreased, like it should come 0.7, 0.4, 0.02, like that, as much as possible. I will try to match this 4 as possible to the actual value. And how this can be happen? This can be happen by doing the back propagation. So this is one is called the forward pass, and while backward pass, what it will do? It will try to adjust. And how it happens? By calculating the gradient. So I hope you guys know about the gradient. So what exactly the gradient is? So how to? So we calculate. Let me write it. We calculate the gradient with respect of trainable parameter. Trainable parameter. So trainable parameters are M and B, your weight and bias. Now, and these are not only in every neuron, there are multiple, but majorly this M and B. Uh, so this gradient actually get calculated. You have to differentiate this M and B with respect of the loss function. So then we calculate the gradient. So differentiation of your M with respect of the loss function. And what will be the loss function? Because since it's a multi-class classification, it means there is a multiple word. So actually it is a cross entropy and multi-class or categorical. So that we will see it on the hands-on. Categorical cross entropy. This is okay. And what gradient means? One other way to think that, so gradient actually measures that for particular parameter. Yes, aim is not categorical. This is the loss function is the categorical cross entropy. The loss is categorical cross entropy, since we are generating the words, right, at every time stamp we are. And for every vector, let's suppose this vector has generated, and for this vector output could be aap, eos, aap, kaise ho, or end of string. Now for this vector, what should be the optimal output? There could be only one, maybe this one for this time, for the next time maybe this one, for the next time maybe that one. So this is a multi-class classification. For binary class we use sigmoid. If suppose it is multi-class, we'll go with the cross entropy. That's a lot. And categorical cross entropy, not binary cross entropy. Binary is for the two class, and for the categorical, it is a for the multi-class, that's a categorical cross. That's a loss function. So multi means if you have more than two classes to identify. Class is the different kind of words. So I'm saying that if suppose your decoder has generated a vector, your this decoder has generated this vector. Now in your vocabulary, let's suppose you have 10,000 words. Now tell me this vector, I have to tell that from this 10,000 which one it should be. So whichever tokens has the, at the index, whichever tokens has the highest probability, that will be the word of that vector. See, if you have to do sentiment analysis, like po- positive, negative, and from this neuron you will have one output. So it will, let's suppose, giving always two vector with two dimension, and here if this one has the highest probability will say positive, if this one has the highest probability it will say negative. So here you will have to calculate the which is called binary cross entropy. But suppose you have to find positive, negative and neutral, so it will generate now three vectors every time. This one is for the positive, this one is for the negative, this one is for the neutral. The same way, every time you will have the vector with the length 10,000. And this is for the word hi, this is for EOS, this is for the word how, this is for the R, this is for the U. And whichever has the highest probability, it will generate that word. Didn't understand. Okay. Okay. So, yes. Now, how you can think for the gradient is what exactly the gradient? Gradient you can understand it is a path. So how so if suppose this is the network, okay, this is here one layer, so this is here, this is here, this is here, this is here, and this is the output, and again this is here, this is here. No, not, let's not do for this neuron, for this. So for every, here there is a weight, this is the weight, this is the weight, this is the weight, this is weight, and in that one bias is also there, one bias, bias, bias. Let's suppose the first time the loss is here, the loss is 10. Now it will start going backward in a back propagation. So it will follow every path. It suppose it has to update this weight. So it will go like that. It will go like this. Now it has to update if this weight. So it will go like this, perform like this. If it has to update this weight, go like this, like this. Now it has to update this weight. So it will go like this. If it has to update this weight, it will go like this. It has to update this weight. So it will follow that every path the way it has came in a forward direction. It will again go in the backward direction. The same way it will try to change this weight and bias so that this one can be reduced. This loss can reduce. And how that loss is getting calculated, that is the formula of the categorical cross entropy. That's why I'm saying it's a loss function. So what gradient actually measures? Gradient measures that for a particular parameters. Let's suppose this parameter. Let's take this two, weight and bias. This part, this two. For a particular parameter, how much exactly these two are, or these parameters are contributing in a loss function? How much actually, and in which direction need to adjust so that loss can reduce. So if you guys have remember or maybe read it, if suppose this is the loss function for the, and when you are doing gradient, let's suppose your loss function is somewhere here. Now the direction is also necessary. You cannot take that parameter here this side. This is the here your, this is the loss function, loss value. So here it is minimum. Okay, this is here minimum. So to take that minimum, you must know the direction. It should go in this side, not at that side. So that is what. So on basis of gradient, we update the weight using the optimizers. So optimizers are there multiple, that we'll see that how to understand the direction. There are multiple, which is called RMS prop or ADA-grad. There are a lot many, but I'm just giving few popular: ADA-grad, RMS prop, ADAM, those things. Okay, so this is how. So teacher forcing, you understand, but while training, that teacher forcing won't work. Let's suppose now you have a new sentence came where teacher forcing, when I said teacher forcing means you are not giving this input to the next. You will give the actual data here to train the model. Whatever you had, that actual data. You will not give the previous timestamp output vector to the next timestamp. Okay. Only you will give the HT and CT, that two things. But whatever that output which will come, that you will not give to the next timestamp to the LSTM. Here I will give my original data. So that is called teacher forcing concept. Why? Because if this output got wrong at that point of time, and if this input I will give to the next timestamp, it is going to hamper the entire training. Okay, it will make the context wrong for the entire one. But now let's suppose when you trained your model encoder decoder, you trained on a huge data. Now you have the new question came. Someone had asked, "Where do you live?" Now convert into Hindi or or Spanish or Tamil or any languages. So in that case, now you do not have actual data. So what will happen to the encoder? You will give this sentence word by word. It will go, and to the decoder, I'm just expanding this decoder. It like this. Here, first it will go start, and whatever it will produce. Let's suppose it produces up. It produces that will go as an input here and the two. If suppose it has produced wrong, now that output you will get the wrong, because if it has produced wrong means you haven't trained your model in with the huge data or with the diverse data or with the proper data, or you have done some mistake in the training. While prediction you cannot perform the what I can say teacher forcing, because for doing a teacher forcing you need the actual data. So how do you need the actual data? For this you do not have. This is the new data came and now you have to convert. But while training you have the actual data, your input and the output you had. So that's why you trained it. And model, why we did? Because I wanted the model to understand in a correct manner. Understand? And one more thing here to improve that in encoder, if this is the encoder, no. So every time we will see in a hands-on, we will put the embedding layer here, and we do not have to embed it every time. We can use the custom embedding layer. For our purpose it will train, or you can use the pre-trained also, like what to wake or globe. But apart from that we can put the embedding layers also, and it will automatically train that. So this is the encoder, and for the decoder also, here we will put the embedding. Okay, because we will pass the words, no, like for English to Hindi, how are you, that aap kaise ho, and that the output will come, and that vector, for that vector here the softmax function will be there, neural network. So the output for the every time stamp will get calculated. So this is how exactly the encoder and decoder works. Okay.